Hey everybody, and welcome back to Algebra 2 Online. So today we're going to talk about a technique that we could use to solve quadratics, but it also is useful for doing one very important thing that you're going to see today. But it's this technique called completing the square. Sometimes in a Algebra 1 class, if you guys are like really crushing material and moving fast, you might get shown this trick, but I'm going to assume that no one really knows what it is. This is technically, like I said, a way that you can solve quadratics, but there's going to be one part in particular that I really want to make sure you see at the end of the video. So make sure you watch until the very end, because there's a part there that's important. So these are 4 questions that are actually going to be useful for something we do today. So I just want to, without a calculator, I want to make sure that you know how to do 2 very important but kind of basic things. And one of them is simplifying these guys over here, which are complex fractions. I have a typo, just saw it. But fraction inside of a fraction. And then just how to solve like really basic quadratics like this. There's like a common mistake that students make here. And we're going to use it today, both of these things, like in the same kind of problem at the end. And I want to make sure that you know how to do this. So the way you do fractions in a fraction and simplify it, basically you kill one of the fractions. So if I multiply, the bottom fraction here, 3/9 by 9/1, I can kill that denominator. So in math, if you multiply by 1, right, I don't change an expression. And so this is what I like to call a funky 1. It's just 9/9, which is 1. But the nice thing is that when I multiply it, I'm going to use a calculator. So 19 times 9 is 171. And then 3/9 times 9 kills the 9s, and you get the 3, right? That actually also is 57. But that is how you could simplify that one. On this one, since the fraction in the fraction is like a 10 on the bottom, I'm just going to multiply by 10/10. This 10 will go away, and I'll get a 3. And then on the bottom, I get a 180, which if you want, you could write as 1/60th. And those are totally equal numbers again, because this part right here is a 1. I just multiplied by 1, which isn't going to change anything with the value of the fraction. So over here, a lot of students want to write 12, or they want to write like square root of 8 for this one. Those are, I would definitely call them wrong. I mean, they're more just partially right, but they're really important that you know the issue here. So 12 squared is definitely 144, but there's another number that squares to 144, and that is -12, right? So we need to stick a plus and minus in here. Same thing down here. If you do, negative square root of 8 on your calculator and you square all that, you will get 8, because the negatives cancel each other out. Negative times a negative is positive. And then the square of the square root cancels and you get the 8. So please remember that if you have quadratics, you always should be getting 2 answers. The only time you don't is actually if it was like x squared equals 0, then here you would just write 0, because plus and minus 0 are the same thing. There's no need to write that. But any other time you have like x squared equals a number, even I, right? Like if we do x squared equals I, okay? Well, no, I don't want to do I. That's actually more confusing. Let's not go there. If you want to know what the square root of -1 is, we can talk, but not right now. But x squared equals -1, we would write x equals plus or minus 1. Nope, sorry, I. So there's still 2 things that you square and get -1, and it's 1i, just I, and it's also -i. So that's important, and this stuff is also important. You'll see it soon. So completing the square is really just an algebra trick, I would call it. And technically it's got like 3 uses. So first, it lets you turn a quadratic into vertex form. And what's easy to do in vertex form? Well, graphing. So whenever you complete the square, you'll actually get, I'm going to kind of jump down here. You'll take a quadratic like this, and it can be converted into this one. This is actually specifically the same one here. And this could be useful for graphing because you could do, the vertex here is -3, -16, and that maybe is something you want to do is graph it or something. So one thing that it's nice for is it does turn it into vertex form. Technically, the technique does also give us a method to solve quadratics, and you might like it for whatever reason more than like factoring or the quadratic formula or graphing, but graphing is always the worst way to solve a quadratic. I personally really recommend you still just stick with the factoring first and then try quadratic formula. This should never be how you solve quadratics. It really is not useful. Like literally if it's an imaginary number, you can't even see the solution with the way that you know how to graph. So you really should just stick with this, but technically if you want, you can complete the square to solve quadratics too. And then one other hugely important reason, but I'm not going to tell you yet. So we're going to do a problem, and it's going to hopefully look kind of familiar, but this is really one of the big reasons I teach you completing the square, the unknown one that I'm not telling you yet. And basically this is what I was just going to kind of, this is the goal for completing the square. We're actually going to take something of the form x squared plus bx, and we're going to turn it into a perfect square. So this is right here, a perfect square. And there's a nice like visual that goes with perfect square or completing the square. And there's going to be a video I post that's regarding that trick too, like how you can visualize what we're doing. It's hard for me to draw it, but this is basically what we're going to do is we're going to take the x terms, so here it would be the x squared plus 6x, and we're going to turn it into a perfect square, right? Because this is a perfect square. X plus b over 2 times x plus b over 2 is x plus b over 2 squared. All right. So completing the square, there's basically 4 steps to it. One of the most overlooked but important steps is you got to make sure that a is 1. This trick assumes a is 1. If it's not, it's easy to fix it because like if this was a 2 in front, well then just divide by 2. And that would fix it, right? So just make sure a is 1, which this one is. So I'm going to just check that off. And then if possible, I would isolate the x terms. So we complete the square only on the x terms. So I'm going to just move the 11 over, just add it over. That way your brain can just ignore the number and you can just focus on the part that you're going to complete the square with. Then this is the magical thing that we add to both sides. And I do have this other video that I want to post and have you guys see why this is the thing that we have to add to both sides. But as long as we add something to both sides of math, right, we don't change anything. So this isn't going to change anything about the problem if we just add it to both sides. That's the really important part, both sides. So b is 10. So in this problem, if I add b over 2 squared, that would be 5 squared, which is 25. And I'm just going to add that to both sides. This just does nothing. It's like I've added 0 in a sense, right? Because I've just like added it to both sides of an equation. It's still balanced out then. Okay, so that's done. Then what you should have in the trinomial being this part, right, is a perfect square. So you actually always should be able to factor it into x plus b over 2 squared. So if you check here, you think about what multiplies to x squared. That's going to be x and x. What multiplies to 25 and then adds to 10? Well, that's 5 and 5. And 5 was my b over 2, all right? So this whole, we can also combine this. So that's 36. But this side over here is x plus 5 squared now, right? And so it's done exactly what I said it would do. We've started with just the x terms, and I added a clever thing. I basically add 0 to the problem, but in a weird way. And then I can get it so I get a perfect square like that. This is my b over 2, and this was my x squared plus bx that I started with. And then this is the reason you can solve problems this way. So you can, it actually goes back to this kind of thing. If you have something squared equals a number, right, you're going to have two things, plus and minus. I'm going to do this in red because it's really important. Plus and minus 6, right? Basically, if you like square rooting here, you can kill the square, but you have two things that you square and get that. You have both a positive 6 squared is 36, and also a negative 6 squared is 36. So there are two things here that you need. And if you only write positive 6, you're going to be really losing like half the points because it is half of the problem that you're missing there. And then you can just move the 5 over. So we get plus minus 6 minus 5. And so the two answers are going to be negative 11 and 1. So even though I am going to show a video that does this a lot cleaner than I'm going to do it, I thought I'd at least kind of in this area show you the idea of what we're doing. So let's say this is a square. So this is my x squared, okay? And then I have another like rectangle over here, and this rectangle is bx. So b is like this distance, and x is this, right? Because x times x is x squared for that chunk, and then this b is like smaller than x. So the idea of perfect square literally just comes from I'm going to try and make this into a square. And so I'm going to still have my x squared, okay? And it was very like rectangular here, so I'm going to take the b x, and I'm just going to chop it in half. Okay, so now this distance, like right here, is b over 2, because it was chopped in half. And this distance up here is also b over 2. And so to make it a perfect square, right, I just need to put this thing in, and then it will be a perfect square. And the dimensions of that right there are b over 2 by b over 2. So this is a perfect little like mini square of b over 2 squared. So in order to get the like full, this is now, just believe me, this is a full like perfect square, let's say, that I started with x squared and bx. I need to add that b over 2 squared in the corner to get it to be x plus b over 2 squared. So I wanted to show you a problem. This is actually straight from a Calc 3 problem that I do, but it's also something that you guys can do right now. So in Calc 3, we work in 3 dimensions, and it's just a coincidence that in Calc 3, you work in 3 dimensions. But this thing is very like messy looking, and it's hard to know what shape it is. But if you complete the square, you can figure out that actually it's a sphere. It's this sphere right here. So that's kind of just to answer this question. But the way to do this is basically you don't have to just complete the square with x terms. You can complete the square with the y terms and z terms. So I'm going to like group like terms. So I'm going to do x squared plus 4x, and then I'm going to leave a little blank here. And then I'm going to do plus y squared minus 6y, and I'm going to leave a little blank here. And then I'm going to do plus z squared plus 2z, and again leave a little blank. And I'm going to move the 6 over because I don't need that to complete the square. I only need the variable terms, okay? So you just go and add b over 2 squared, and b for x is 4. So 4 over 2 squared, so that's going to be 2 squared really, is 4. And then I have to keep everything balanced, so I add it over there. B for the y terms is negative 6. Negative 6 divided by 2 is negative 3. Negative 3 squared is 9. So I'm going to add 9 over here. And then last but not least, 2 for z is my b. 2 divided by 2 is 1. 1 squared is 1. And so if I add 1 on that side, this is the exact same equation, but now I can factor things. So the blue, x terms factor into x plus 2 squared. The green ones would be y minus 3 squared. The z ones would be z plus 1 squared. And then over here, the numbers all combine to 8. And this, should kind of look believable that it's a sphere, because in like geometry you learn that like if you have something like x plus 2 squared plus y squared, let's say, equals 16, that this is a circle, right? There's a big circle unit in geometry, and the center is negative 2, 0, and the radius is the square root of the 16, which is 4. So if you kind of like keep that in mind, the center and radius of this thing would just be, so the center is, it's always just the opposite of the numbers in here. So it's negative 2, 3, negative 1. And then the radius is the square root of this number. So we can literally just write the square root of 8. Now it's hard to see some of this, but this is a cool online 3D graphing program called math3d.org. Awesome website, super good. But you can see I just plugged in the original thing, but it's hard to see, but this is the x-axis, this is the y, and this is the z. And truly the, negative 2 and the x kind of back there, and then 3 comes out, and then negative 1 drops down a little bit. The center of this ball is really that spot, and the radius is square root of 8. And if I asked someone to just look at this and tell me these two things, that would be like really hard. But if you know how to complete the square, then you can turn it into this form, and you can see the center and the radius and all that just from right here. All right, so now comes time for the big problem that I really wanted to do with completing the square. So we're talking about quadratics, and I said that I don't really want you to solve quadratics using completing the square, but this is one time I'm going to break that rule. So I am specifically here asking you to complete the square of the general standard form quadratic here, ax squared plus bx plus c, and I want you to solve it for x, okay? And so to complete the square, first step, make sure a is 1. Right now it's just a, so we'll have to divide everything by a in order to make sure that is a 1 there. All right, we only complete the square on the x terms, so I'm going to move the CA over. And then completing the square, you're going to add b over 2 squared, right? And I'm going to do this kind of off to the side here. B over 2, sorry, b is b over a. So b over a over 2. This is where the complex fraction part comes in. If you multiply top and bottom by a, which is like a 1, right, you're going to get b over 2a. So this is what I add squared to both sides. All right. We know that we just completed the square over here, so this thing should factor into x plus b over 2 quantity squared. So this purple b over 2a is my b over 2 here in this problem. So this side is just going to factor into x plus b over 2a, all of that squared. And I think I'm just going to copy this over for right now. And I'm going to square this. So b over 2a squared is just b squared over 4a squared. Right? So I'm going to take, I'm going to just combine this now, I think. So I need to get a common denominator. So the common denominator, there's a in both, but this one has a squared, so basically 4a squared would be the common denominator, right? So I'm going to just multiply the left one by 4a. So I'm going to get minus 4ac all over 4a squared, right? Plus b squared over 4a squared. And then I have a common denominator, so I can combine those two fractions now. And I'm going to combine it in a certain way. So the denominator is the same, so I can just add the tops, right? But I'm going to specifically put this and then this. It's the same value, and you're starting to maybe see where this is going. So I've got this b squared minus 4ac, that should look familiar, all over 4a squared, okay? Now I'm going to pull in another thing from before. So we know that when we have something squared equals a number, which is what this is, we're going to get plus and minus. We're going to get two things that you can square and get that. There's we did one earlier where it was 6 squared is 36, but also negative 6 squared is 36. So if I kill the square, right, I'm going to get x plus b over 2a equals plus or minus the square root of b squared minus 4ac all over 4a squared. Then I'm going to simplify I'm going to give myself a little divider here. The top of that square root is not super nice, so I'm just going to write that. But the bottom is actually a perfect square, right? If you do the square root of 4a squared, you get 2a, right? And so the top you just have to leave, but the bottom is now 2a. And then you probably see where this is going. I'm just going to subtract b over 2 to the do a to the other side. And I'm going to do just one more little step. I've got common denominators here, so I can just combine those common denominators. Actually, this is the punchline. Let's do this in red here. So I'm going to combine my fractions, so negative b, and then plus or minus the square root of b squared minus 4ac all over 2a. So this is actually how they did it years and years and years ago. But if they realized this technique of completing the square, and really the story goes, they actually started with this kind of geometric idea. It came out of geometry. And then they realized, oh, this applies to, a lot of stuff in algebra. And so they took a general quadratic like this, and they just cranked through exactly what we cranked through, and they get the quadratic formula. So when you use this thing, you're basically solving a quadratic with completing the square. I always view them really the same way. It's just like, it's a shortcut almost. That's really what a lot of formulas are, but it's basically just going through completing the square to solve a quadratic, but you just get it in one step, basically, by just having this formula to plug in. So this is what everyone remembers in Algebra 1, but technically, it's just completing the square. So that's hopefully makes some sense. It's a very kind of famous problem in math, and if there's any steps that don't make sense, please ask.